This video is part of a video course on the xv6 operating system kernel. There's a lot of code involved with the file system, and I've broken it up into a number of different videos. So far, I've already talked about the buffer cache system and the disk logging system. In future videos, I'll talk about the code, but in this video, I'm going to focus on how the file system is represented on disk. So in this video, I'll talk about the disk organization and layout for directories and files. Previously, when I talked about the logging system, I showed this schematic image of the disk, where each one of these squares is a block on disk. And we had some stuff, including the log area, as well as a main block area. Let's simplify that picture and just look at the disk block area. So we just have a sequential set of disk blocks on the disk, and the code that we've looked at already provides a number of functions that we can use to access these blocks. And here I'm showing what it would look like in the code to access the blocks on the disk. In particular, we have the function bread, which can be used to read a block in from the disk, and we provide a block number, and it allocates a buffer from the cache and just reads the disk block into memory and returns a buffer pointer, a pointer to that buffer in memory. And then we have the log write function, where we provide a pointer to a buffer, and it will write that buffer's data back out onto the disk. We can read or update the data in that buffer anytime after we call bread. And we can call log write multiple times, so we may write it and then modify it some more and write it again. When we're done with that particular buffer, we need to call this function brelease, and between the bread call and the release, the buffer will be locked, which enforces the fact that we have exclusive use of that buffer. Only this thread can access that particular buffer. Now, a collection of writes are included in a transaction. The call to begin op signals where the transaction begins, and at the end of the transaction, we should invoke this function end op. There can be a number of calls to log write within the transaction, either to the same buffer or to different buffers, and those are all grouped together. And the logging system will enforce the fact that either all of the writes within the transaction are performed, or none of them are. So it's an all or nothing situation. A file system contains a single tree of directories, as well as a bunch of files that are located in those directories. And all of these are on one single device, like a disk or a USB drive. The directories are organized as a tree. That is, there are no cycles, and it's not a DAG. A DAG is a directed acyclic graph. So here's an example of a file system, and I've shown the directories in red and the files that are not directories in green. And you can see that if you just look at the red, it is a tree. In other words, every directory has a single parent except for the root. The other files that are not directories are shown in green, and in some cases you can see that some of these files have multiple parents. And of course, you remember that we refer to files by their path names. The file itself does not have a name. Instead, we refer to it or access it based on its path name. So for example, this file here could be referred to as /a/f/k, or we could also refer to the same file using another path name. Every directory is itself a file, and so we have several different types of files, both directories and regular files. In xv6, we also have a file type called device. In fact, there's only one device that is located in the directory tree, and that is the console. But in general, we could have other devices as well. Those are the only three types of files that xv6 implements. But Unix systems and Linux systems implement other types as well. POSIX is the standard for Unix and Linux systems, and it specifies other kinds of files. So we typically see devices. We have two different kinds of devices, actually. We have a character device and a block device. We also have symbolic links, which are sometimes called soft links. We have named pipes and sockets, but none of those are available in xv6. And as I said, files don't have names. We use path names to refer to an individual file. I want to take a moment to talk about the difference between hard links and symbolic links. Symbolic links are sometimes called soft links. Just to be clear, xv6 and every Unix and Linux system implements hard links, but xv6 does not implement symbolic links. So a regular file can have multiple hard links pointing to it, that is, multiple parents. And in my example here, this file has multiple hard links that refer to it. In other words, this file can be located as an entry in both this directory and this directory here. Every directory, on the other hand, has exactly one parent, except of course the root node. So each directory can only have one hard link pointing to it. That is, the directory tree has to be a tree, whereas if we include the other files, we have a directed acyclic graph. So in xv6, we have regular files, directories, and devices. Symbolic link is another kind of file, and that's not included in xv6, but it is a type of file. So what's going on with a symbolic link? Well, we have a file, okay, but the file doesn't contain data. It contains another path name. And when encountered, the kernel will automatically use that path name to locate what we can call the target file. So for example, this file here might be a symbolic link. Okay, it doesn't contain any data directly, but instead what it contains here is a path name. So if we refer to this file, okay, with a path name ch, what the kernel will do is it will go down and see that it's a symbolic file, a symbolic link, and it will then use that second path name, which might refer to, let's say, this file over here. And then instead of accessing the data here, when you do a read or write, for example, you'll be reading and writing data from this file here. Now, a path name is with hard links is either valid or invalid. Okay, if we say CG, we get to this file. If we say CB, there is no B entry in this directory, so that's a bad path name. We have another situation with symbolic links. A symbolic link can become broken. Okay, so we might have a perfectly valid path name to get down here, but the path name here might indicate a file that doesn't exist. It might be a bad path name. With hard links, the files must be on the same file system or within the same file system as the directory that points to them. So everything is in or on one device with the hard links. One advantage of symbolic links is that the path name can point to a file that's on another device in another file system. And we can run into problems if we try to trace down or locate and follow a symbolic path name that is located on a file system that's not even available. So that's another thing that can go wrong with symbolic links. Next, I want to define the terms inumber and inode. As you know, user mode programs refer to files with path names, but the path names aren't necessarily unique and they can change. Instead, the kernel uses a number to identify and work with files, and that's called the inumber. It's a small integer, and it's assigned to the file when that file is created, and throughout the life of the file, its inumber will never change. After the file is deleted, the inumber is no longer needed and can be recycled or reused for a new file, and that also happens. And it's also the case that the root directory has a fixed and known inumber, and that number is 1. This is a mistake. The inumber of the root is 1 so that the kernel can locate the root directory. And files are numbered from 1, not from 0. The inumber of 0 is reserved to indicate an unused directory entry. Associated with every file are a number of attributes. The most important one is the inumber, which is used to uniquely identify each file. The type tells which kind of file we're dealing with. In xv6, we can have a directory file, a regular file, or a device. In other Unix and Linux systems, we have other types as well. Directories and regular files contain data, and so if we have a directory or a regular file, we need to know how much data we have, and so we have the size in bytes of the data. We also need to keep track of how many hard links point to this file. Okay, that's the number of parents in the tree. For example, this file has 2 hard links pointing to it. If there were no hard links pointing to it, then there is no path name by which we could refer to a file. And so we can think of the number of hard links as a reference count. When the number of pointers to an object goes to 0 in an object-oriented system, the object space is reclaimed by the garbage collector. Well, a similar thing is going on with the xv6 kernel. When the number of hard links goes to 0, the kernel will automatically delete the file. In the case of directories and regular files, there is additional data, and so we need to know where on disk that data is stored. So we basically have a list of the block numbers that contain the file's data. In other systems, not in xv6, but in other Unix, Linux systems, we have additional information, including the timestamp of when the file was created and when it was last modified and so on. We also have information about who owns the file and some bits that indicate the permissions and to tell how other users can access this file. The attributes are kept on disk in a small fixed size structure called the inode. Okay, the inode is kept on disk. It's not kept in any file, but these are kept in a separate area of the disk. So somewhere on the disk there is essentially an array indexed by inumber of these inode structures. Whenever a file is in use by the kernel needs to read in the inode structure from disk and keep it in memory. So the kernel maintains a cache of inodes in memory. So let's take a look at how the inode structure on disk is defined. So here we have a structure that shows the on-disk inode. We don't see the inumber. As I said, these things are kept in an array that's indexed by the inumber, so the inumber is implicit. The type field tells what kind of file this is, and we have several constants to indicate whether it's a directory, a regular file, or a device. We also use the type code to indicate whether the inode is free. So some of the inodes on disk in this inode array are in use and have a type of directory, file, or device, but others are free and unused and available for future files, and we use a type of 0 for those. If the file is a device, then we also have the major and minor numbers being valid. And what are the major and minor numbers? This is essentially the device number. So the device number is a 32-bit number, and it's broken up into 2 16-bit fields, the major and the minor number. The major number is an identifier to tell what kind of device it is, and the minor number tells which device among several it is. For example, if we have 3 Hewlett-Packard printers, the major number would indicate that this is a Hewlett-Packard printer, and that will be used to indicate what routines we should use to access the printer. The minor number would tell whether this is printer number 1, 2, or 3, or whatever. Then we have the number of hard links, and then we have the size in bytes if it is a directory or a regular file. And finally, if it is, we have the blocks on disk where that data will be kept. So this is an array of block numbers here. Previously, when I talked about disk logging, I presented this schematic diagram for what the disk looks like. And I just had the main block area here. But now I want to present another view of the disk that is more accurate and more detailed. Let's go through this thing. The boot record is a block that is neither read nor modified by the kernel. It's used just during the boot and startup process in order to load the kernel into memory. The Superblock contains a number of parameters. It is read by the kernel, but not modified. Among other things, it tells where the other items on the disk are located. Then we have the log, which I talked about elsewhere and won't go into any more detail on here. Then we have an area where the inode structures are stored. We have the bitmap and we have the data blocks. Remember that each inode is stored in a fixed size structure, and these are packed into an array, and this array is kept in these blocks. A small number of inodes will fit into each block, so depending on how many inodes we have, including both the ones that are in use and the ones that are free, we have a number of blocks that are allocated to the storage of inodes. And then we have a bitmap. The bitmap contains one bit for every block on the disk, and that bit indicates whether that block is in use or free. It's really useful for the data blocks. Okay, we consider all of these blocks up to this point here to be in use. So the bitmap will indicate that all of these blocks up to this point are in use, and all of these blocks here are either in use or free, indicated by a bit in this bitmap. Okay, so there's one bit for all of the blocks. In this particular file system, we only have 1,000 blocks, so this bitmap would only be as big as required to contain 1,000 bits. That'll all fit into one block, of course, but I've shown 3 blocks here for illustrative purposes. And the bit is either 1 to indicate the block is in use or 0 to indicate that it's free. And finally, we have the data blocks. This is where the files and directories are actually stored. Now let's look at the superblock. The superblock is essentially a block that contains this structure here, and the structure has a number of fields. Okay, so let's see what's stored in this block on disk. First of all, we have a magic number. This is just a constant, and the operating system, when it reads in the superblock, will check this number to make sure it has the right value. And if it doesn't, that might indicate that, wow, this is not the kind of file system we expect, or something is dreadfully wrong. This disk doesn't contain a file system at all, or something else is really the matter. The size field, in our example, will be 1,000. It tells how many blocks are available on the disk. Okay, the number of data blocks is 959 in our case, so we have that many blocks here. And we have 200 inodes. So how many blocks is that? Well, the kernel will compute that and figure that out. But in any case, we have enough space to store 200 inodes. And that means that this file system can accommodate up to 200 files. We cannot have more than 200 files. In log is the number of blocks that are allocated to the log, and then we have an indication of where that starts. It starts at block number 2, and then where the inodes start, block number 32, and then where the bitmap starts, block number 38. The size of the bitmap will be determined by the number of blocks, and as I said, with 1,000 blocks, we can actually fit the bitmap into a single block, but I've shown 3 here, even though that wouldn't be the case. So this superblock is read in from disk at startup by this function read sb, and then it never changes. And so here I have the structure that contains these, and you see this is exactly what we saw before. We have the magic number, we have the size, in blocks, the number of inodes, the number of blocks in the log, where the log starts, where the inode blocks start, and where the bitmap blocks start. And so that's read in at startup time. In my example file system, I showed the edges as being labeled, and that is important because it emphasizes path names. But that might not be the way you think of directories. Here I'm showing the edges labeled, but you might think of it as a directory containing a bunch of names, and those names each refer to a directory or file somehow. Well, directories are stored in files. So for every directory, there is a file, and that file contains a number of blocks, and the directory information is stored in those blocks. Here's what we have in xv6. In xv6, a directory is represented as an array, and each array entry has both a name and a reference to the file. The name has space for up to 14 characters, and the reference to the file is an I number. The original Unix system had this 14 character limit for file names. In xv6, we can have up to 14 characters for the file name, and if it's shorter, we would terminate the file name with a null character. When we want to look up a file, we have to go through this array linearly, and that's a bit time consuming. In modern Unix and Linux systems, we have a different organization for directories that will accommodate longer file names. And as you know, some directories contain hundreds of files, so we have different data structures that allow for faster lookups. But essentially, it's still the same idea. You have a name, and for each name, you have an I number. So that pretty much completes the information about how the file system is stored on disk. So next, let's take a look at how the mkfs function or program, which can be used to create or build a file system from scratch. mkfs, or make file system, is a standalone C program. It's not part of the xv6 kernel, and it's not a user mode program that runs under the xv6 kernel. Instead, it's a separate C program. It's compiled on your host computer, and it runs on that computer just as the QEMU emulator runs on that host computer. When you run the makefile, it compiles the xv6 kernel, and it compiles all of the user mode programs, and it also compiles this mkfs program and runs this program as well. And what does this makefile system program do? Well, it's going to create the disk image file. The disk image file is named fs.image, and this is a file on the host computer, and it will be used by QEMU to emulate the disk. So all of the contents of the disk are kept in this file system image file, and whenever a read or write command is issued to the disk, QEMU will actually go to this file on the host system to get or put data. So our disk in xv6 is initialized to have 1,000 blocks, and each block is 1,024 bytes. So that means there is 1,000K bytes in this file, 1 byte in the file for every byte on the emulated disk. Makefile system will initialize the disk. Okay, it will create the entire file system. It will create the directory tree, and it will put a number of files into the directory tree so that when the kernel begins, that is at startup time, the kernel will find the file system already exists. So what does it do? Well, makefile system will write the Superblock to the file, or that is to the image file actually. It doesn't write anything for the boot record because that's not really needed. And it will also initialize all the inodes. It will initialize the bitmap area of the emulated disk. It will create a directory structure and initialize some directories. And for each of the user files, that is the user mode executables like cat, echo, the initial program, the shell, and so on, it will create a file and add that to the directory of the file system. So that when makefile system is done, this image file will contain an entire complete file system ready to go so that the kernel can boot up and find the file system. Real Unix and Linux systems also have a similar program called makefile system, and these will initialize not an image file but a device, and they will write whatever is necessary to initialize the organization for the file structure on that device. The file system organization that we've talked about for xv6 is fairly simplified, and these makefile system programs for other systems will create file systems with very different and more complex file systems. But so these are complicated programs to create the initial file system on a device. But in any case, the makefile system program that we are looking at here in xv6 will make use of some parameters we'll go to the file param.h and get things like the file system size, that's the number of blocks to create in the file system, as well as the number of blocks to add to the log. And we also have a number of predefined parameters or macros and constants. For example, the number of bits per block that we can store for the bitmap, or the number of inodes that we can pack into a block in the inode array that will be represented on disk. These constants are needed by the makefilesystem.c program to create the image file. Okay, that wraps it up. I'll see you in the next video.